Hello, my name is David Tu, and I'm a Program Director at RPE. I would like to speak with you for a few minutes about our ML for Design-related program, Differentiate, or more succinctly, D'. At present, RPE is investing $35 million to support 23 teams in the development of design tools that leverage the transformational power of machine learning. We hope that the development of such tools will help engineers to be more creative and productive, enabling them to design better energy products faster. By doing so, we hope to accelerate RPE's mission of reducing our nation's energy usage and related emissions, thereby helping to mitigate our impending climate crisis. A simplified design process framework has been used to define three desired capabilities for enhancement. A problem is posed, engineers hypothesize the solution, and then evaluate it via numerical simulations or physical experiments. They then update their designs and iterate until a solution is developed. We seek to develop both enhanced hypothesis generation and concept evaluation capabilities. Our hypothesis tools may take the form of ML optimizers that have been trained with domain-specific data, resulting in a hopefully more efficient, albeit domain-specific capability. On the other hand, our evaluation tools may take the form of ML-based surrogate models that can make instantaneous performance predictions once trained with data from physical simulations or experiments. Ideally, we would of course prefer to get our designs right the first time to avoid the cost of iteration. To this end, we are seeking to leverage the expressive power of deep neural networks to express designs as explicit functions of their requirements. Once trained in the forward direction, these inverse models will ideally be capable of instantaneously generating near-optimal designs for requirements. In the next several slides, I will discuss each of these three capabilities in more detail. To start, surrogate models in the form of deep neural networks or Gaussian processes offer the potential for effectively instantaneous high-fidelity performance prediction once trained. Within Differentiate, both numerical simulations and physical experiments have provided the data used to train surrogate models for a given application. While we expect that these models will offer tremendous value in otherwise traditional design processes, they've also been critical in the D' program to the development of hypothesis generation and inverse design capabilities. We have been exploring the use of ML as a potential optimization accelerator for hypothesized potential of ML algorithms to learn domain-specific characteristics of design solution spaces. Multiple approaches are being pursued, with reinforcement learning being a technique employed in some of them. An RL example is illustrated on the slide, where our domain expert optimization agent repeatedly interacts with our surrogate model-based world to ideally develop the ability to find near-optimal solutions more rapidly than generic tools might be able to do so. However, while there are multiple examples from the program where RL methods have been demonstrated to work, a full value proposition assessment, inclusive of training costs, versus traditional techniques is still pending. The last capability that we are seeking to develop is the ability to execute inverse designs via generative models. That is, we would like to instantaneously generate near-optimal candidate designs from requirements. Several ML approaches are being employed, including GANs, normalizing flows, and invertible neural networks. These methods are trained in the forward direction, and once trained, the networks are inverted and used to automatically generate designs from requirements. These inverse methods have transformative potential through their ability to enable the realization of custom designs at extremely low cost. Over nearly the past 2 years, 23 talented and hardworking teams have been working to develop these three capabilities for 7 challenge problems. We've been trying to develop the ability to automatically architect system designs, including electrical circuits, molecules, crystal structures, and thermochemical processes. We've been developing surrogate modeling tools for battery materials, HVAC systems, aircraft compressors, boiling heat transfer, and additive manufacturing producibility assessments. Lastly, we've been developing inverse design representations for wind and gas turbine blades, aircraft wings, organic photovoltaic devices, photonic devices, and optical metasurfaces. While we are still in the process of distilling the lessons that we've collectively learned during the D' program, and are working to define next potential investment steps, I think it is easy to say that ML-based methods clearly work for each of the three design capabilities sought. However, as we move on to more real and complex / higher dimensional problems, the cost of training our methods increases dramatically due to the need for both more data and more expensive data. Given the scaling challenge, an active research topic is to understand how to lower the cost of acquiring this training data via a range of techniques that include transfer learning, multi-fidelity models, and active learning. Lastly, I think that additional work is required to obtain the data necessary to quantitatively assess the value proposition of ML-based methods in some of our target application areas. This being said, I've been amazed by the progress that our 23 teams have made and I'm looking forward to watching as these methods transform the way in which engineers design advanced energy technologies and products. Thank you very much for your time.
Hello everyone, my name is Leno and I will present our paper entitled Deep Symbolic Optimization for Electric Component Sizing in Fixed Topology Power Converters. Power converters are a major component in any of the current electronic hardware devices. And for developing new power converters, this is a very tedious and very manual process in which the expert has to use a lot of experience to find a topology that works and it's efficient. So what we are doing in this paper is proposing an artificial intelligence method for autonomously build converters starting from a desired topology. And the way we approach this problem is by modeling it as a symbolic optimization problem, which basically means that we have to represent the circuit as a sequence of tokens, and those tokens will be the electric components. So each sequence of tokens will be related to the efficiency of this resulting circuit. So what we want to do in the symbolic optimization problem is to find the sequence of tokens that is related to the best efficiency possible. So we have to evaluate different circuits and find the one that has better efficiency. And by modeling this problem as a symbolic optimization problem, we can leverage the state of the art in this area. So we are starting from the Deep Symbolic Optimization algorithm, or DSO, that uses an RNN allied with a token tree representation to learn how to optimize those sequences. Visually, the way this works can be observed here in this slide. We have a token tree that will represent the circuit, and each of the tokens will either be a way in which components are linked or the components itself. So for example, parallel collections, serial collections, we have like voltage, MOSFET, inductor, components, and so forth. And it's very easy to translate from the token tree representation to an actual circuit representation. And we can do this fairly easily. And the way we do is by like using the representation number 1 to train the algorithm and to sample new topologies. And then those can be used in the representations 2 and 3 that are more interesting for humans. So in our proposed algorithm, we'll be able to sample sequentially those components, and the RNN will output a categorical distribution for each of the possible tokens that can be sampled. Those tokens will be sampled one of each time, and over time, the RNN will be trained using sampled circuits and their respective efficiency. So the RNN will be able to sample better and better circuits until it finds the optimal one that will be used. In order to evaluate our approach, we compare it against 3 different algorithms. Brute force, that will be basically manually searching for every combination of circuit, Q-learning, and DDPG, that represent regular reinforcement learning algorithms. What we see from our experimental results is that DSO is able to find the optimal topology that can be found from the available tokens that the algorithm has access to in all of the 4 evaluated topologies. And it does so using a way shorter period of time than the other competing algorithms, which are like brute force, Q-learning, and DDPG. Another very interesting thing that was discovered by us when we were running the experiments is that for the buck converter, we can see in this first graph that the highest performing topology is the one that has higher frequency. And as we are reducing the frequency, it reduces the efficiency of the circuit. So this is a very interesting result in the point of view of the application for enabling the experts to find more efficient circuits. As a conclusion, we propose a method that represents power converter topologies as sequence of tokens, and we showed that by doing this, we are able to find optimal solutions way faster than the other state-of-the-art reinforcement learning approaches. For future work, we want to extend this for generating new topologies autonomously instead of having to be restricted to a single topology.
Hello, my name is Malik Hassanali. I work at NREL, and I will present on an improvement of importance splitting for low probability estimators. For design and manufacturing, rare events, manufacturing defects or extreme loads are typically to be avoided. Estimating the probability of such rare events is useful for conducting risk analysis or anticipate cyclic fatigue. The problem we are interested in is shown on the top right. Given a dynamical system that governs the dynamics of a variable xi, we are interested in tracking the some quantity of interest q of xi. While the system is deterministic, it is characterized by some form of uncertainty, for example, in the initial conditions. So what we would like to estimate is the probability of the quantity of interest q to reach an extreme level at the final time capital T. One way to estimate this probability is genealogical adaptive multi-level splitting. And here what we do is that we run an ensemble of realizations. Intermittently, the realizations are replicated if they are headed towards the rare events, so that we can increase how many rare events are observed and reduce the variance of the probability estimator. The steps that we're interested in here is cloning. Replicating deterministic system is not as easy as copying the state of the system. One needs to introduce some level of perturbation that differentiate each one of the offspring of each parent realization. And typically, cloning is done by adding a random perturbation at every replication step. We notice that in Hamiltonian type of system like Lorentz 96 equation, where particles may be disorganized, random cloning works pretty well. However, in spatially coherent cases like Kuramoto-Sivashinsky equation, this method can fail. In the bottom panel, the black lines are the CDF of the Q of I obtained with a Monte Carlo estimator, and the blue line is the probability estimator, the importance splitting probability estimator value. The dashed line shows the variance of each estimator. And what you can see is that in the Kuramoto-Sivashinsky case, random cloning virtually does not achieve any variance reduction compared to Monte Carlo. And our hypothesis is the following. Perturbations need to be consistent with the system dynamics. In particular, spatially coherent perturbations are necessary for spatially coherent systems. The core idea here to solve that problem is to use a generative model for generating appropriate perturbations. Our method consists in two ingredients. First, we use a conditional GAN that is conditioned on the quantity of interest that generates new system states. At each replication step, we may need to create multiple clones, so we need to ensure that we did not enter a mode collapse. And to this end, we use a diversity loss that forces the diversity of the generated samples. Second, the perturbation applied to the dynamical system effectively change the dynamics. And so what we need to do is to mitigate that effect by selecting perturbations that are not too far away from the parent realizations. A key element here is the data source. Here what we do is that we leverage the fact that we have a statistically stationary part in the dynamics that is highlighted in the red box on the right, so that we can run a few realizations at first and then sample the state multiple times during a single realization to collect enough data. Here are the results. So on the top right, you can see the comparison between random cloning and a GAN-based cloning. The offspring, that is shown in blue, exhibit much more strong spatial coherence than the GAN for the GAN-based method than with random cloning. And it does that while still generating offspring realizations that are close to the parent realizations. In terms of computational gain or variance reduction, the performance of the approach is shown in the graphic below. Random cloning for Kuramoto-Sivashinsky equation did not achieve any variance reduction, as you can see in the dashed blue line. However, with the GAN-based approach, which is the solid blue line, we actually managed to reduce the variance, so increase the computational gain. And we actually, interestingly, increased the variance all the way to the level that is achieved with the Lorentz 96 equation. So that suggests that the approach that we proposed bridged the performance gap between spatially coherent and incoherent systems. So what does this mean? The difference in performance between the Lorentz 96 and Kuramoto-Sivashinsky equations can be explained by the cloning procedure, which means that cloning does matter for genealogical importance splitting. and that realistically looking perturbations are the way to do it. A tighter control of the perturbation magnitude will be implemented as future work, and we'll try to identify systems that can also benefit from a similar approach. And with that, I thank you for your attention.
Kelly Marshall. I'm a PhD student from New York University, and today I'm going to talk about differentiable design with dynamic programming. So in many design problems, we want to be able to specify certain attributes of the data point or example that we're designing, where that attribute is defined as the solution to some combinatorial optimization problem, which can only be efficiently solved with dynamic programming. So on the bottom here, you see two examples. One of a game design problem in which the attribute of interest is the shortest path to the final boss or monster, which is defined using some variant of the Bellman-Ford algorithm. And on the left, similarly, you see photovoltaic microstructures, which we'd like to be able to design while controlling the shortest path that electricity could take through the microstructure itself, as this sort of controls for the conductivity of the material that we're designing. So for background information, one work that we very much relied on in doing this was previous formulation of differentiable dynamic programming approximations. So dynamic programming algorithms consist of iterative updates with either a maximization or a minimization. This maximization, at each step, it introduces non-differentiability into the dynamic program because when the arguments are not unique, the derivative is not defined. So what previous work has done is define some smooth max operation by adding a convex regularizer to the max function. This gives us an approximation of the max function, which we can substitute into the dynamic program. By making this repeated substitution, this repeated approximation, we can get an approximation of the overall dynamic program value, V, which is the optimal cost for solving the program. However, one problem that we run into in applying this in the context of design, where we'd like to differentiably specify attributes so that we can enforce these constraints on attributes, is that as the number of steps taken in a dynamic program increases, the approximation given becomes increasingly inaccurate. And we find that it makes it very hard to enforce these constraints. So what we instead do is in the forward pass compute both the true value of the attribute as well as the approximate value of the attribute, which we're able to use to get a suitable gradient. So you can see in the case of these generated microstructures, the number of DP updates needed in order to compute the shortest path values that we care about is on the order of 2 to the 12th. So it's very important that we not have a extremely biased estimation of the gradient in order to get good results. The next major contribution of our paper is this solution gradient formulation. So in many piecewise regression problems, dynamic programming can efficiently solve these problems by finding the correct partitioning of an input signal and fitting a piecewise approximation to it. But previous formulations of the Jacobians of these operations just sort of fixed the partition locations in order to get a suitable Jacobian, which doesn't allow for the input to be updated in such a way that the partitions will change, making it sort of less flexible and less practically usable in some of these design scenarios. So our work sort of is able to take a weighted average of these different Jacobians over a probability distribution given by the differentiable dynamic program in order to give a more flexible Jacobian formulation. And finally, these are our results on the histogram differentiation and microstructure generation experiments. So in the histogram case, we find that our methodology is able to update a signal so that its histogram approximation will exactly equal a target that we set for it. So this allows us to design a signal which has certain histogram attributes. Furthermore, in the case of microstructures, we find that our formulation of the D-bias soft TP is very important in minimizing shortest path error. So here we're able to generate realistic microstructures that have controllable shortest path attributes and are synthesizable.
In this presentation, we'll be talking through AI-driven design space exploration for thermofluid domains. My name is Katie Kirsch, and I'm presenting along with Amit Bhatia, Claudio Pinello, and Ram Ranjan. We're all from Raytheon Technologies Research Center. And we've chosen this topic of the design of thermofluid domains or components because the design of these components is complex and it's challenging. And it's a topic that's well suited to AI methods. So when we talk about thermofluid domains or components, what we're speaking of in this particular context would be heat sinks or cold plates. Both are used in the thermal management of a variety of industries. A couple to highlight would be the power electronics industry and the energy storage industry. So as electronics packaging gets even more compact, electronics can experience much higher temperatures, and then the heat sinks need to dissipate higher heat loads within smaller volumes. And so where do you begin in a design challenge like that? A conservative way would be to begin where you left off. So what has worked in the past, and you can make small incremental changes to those designs. But what you'll get then are only incremental changes to the performance of your heat sink. And when you want to talk about revolutionizing an industry or completely changing, making a step change in performance, you need to think about the design a little differently. And that's how what we're approaching with our AI-based design tool.
Hello everyone, this is Amit Bhatia. And I'll be walking you through the rest of the presentation. So as my colleague described in the previous slide, the design problems for thermofluid domains are complex, the design spaces are large, and if you want to improve performance beyond small increments, then we also need to look beyond making small changes to existing designs. And at Raytheon Technologies Research Center, we have been developing a requirements-driven AI design framework. It's a multi-step approach that tries to combine our knowledge of existing design techniques together with some AI-driven techniques that we have developed in-house to come up with good design choices. So it consists of multiple steps. In first step, we create a corpora of candidate designs, again, using variety of approaches. The second step is where we ensure that the generated designs can be manufactured in practice. The third step is where we try to learn design choices through a variety of machine learning approaches. So examples of design choices could be, for example, what type of channels do we want to have? How many channels do we want to have? The fourth step is where we are given a new design problem on the domain. And now we use the trained machine learning based models to come up with feasible designs, which we expect or actually want to be also close to optimal performance. Our proposed framework offers multiple benefits. First benefit is that we can do design exploration at scale through automation. A second important benefit for us is that we have heterogeneity in the exploration process through heuristics. And a third key benefit that our approach offers is that we are able to incorporate domain knowledge that could be coming from a variety of different sources into the design exploration process. So thank you for your attention, and we are happy to take questions, and we are always looking for collaboration opportunities as well. So please do reach out if you have any feedback on improvement, or if any ideas you think could be leveraged here in the overall framework, and perhaps lead to some collaboration opportunities on this topic.
The most common aerodynamic shape is the aerofoil. Usually it's represented as a closed curve, but typically it's given by the points along this curve without explicit knowledge of the curve itself. If we put these points coordinates in the matrix such that each row represents the point, then we will get the n/2 matrix represented aerofoil shape. This aerofoil shape can be input to the given computational model, and the output can be a deterministic quantity of interest from this model. For example, on the background here, you could see the pressure field for the flow around the aerofoil. Our goal is to define the input domain for this computational model. And the problem is that each computational task F is very sensitive to the choice of input parameters. And we want to design a data-driven shape parameterization, which respects a priori physics-based problem knowledge. For example, we know that the coefficient of lift shown here on the y-axis is very sensitive to the change in the camber. We also know that the changes in characteristic lengths change the Reynolds number, changes in thickness change the drag the most on average, and the rotation is just redefine the angle of attack. All these changes mentioned on this slide can be represented as a affine transformation. If our shape is represented by a matrix X, the affine transformation is just right-hand action on X plus some shifting. So the question is, how can we define undulating perturbation common to the manufacturing, independent of the important and often constrained affine deformations? We suggest using the Grassmannian manifold. It can be described as a space of n/2 matrices, modular affine transformations. The elements of the Grassmannian are decoupled from the important affine deformations, and we can define them using the landmark affine standardization. After we decouple the Grassmannian shape and the affine transformation denoted by M here, we can infer parameterization for this Grassmannian shape using the dataset of discrete aerofoil shapes and the principal geodesic analysis. The principal geodesic analysis is just generalization of the principal component analysis for the Grassmann manifold. The procedure is listed here on the left, and the result is shown on the right, where we truncated the inferred parameters up to 4 the most important based on the singular values. We can compare our PGA parameterization with the state-of-the-art parameterization for aerofoils, the class shape transformation, CST representation. For that, we created the data set using the 16 baseline aerofoils from the 3 different turbine blades. And we fitted the CST representation to those aerofoils and then performed the 1000 perturbations to these CST coefficients by up to 20% for each baseline aerofoil. You could see on the left here that the domain for the CST representation is very disjoint, which can cause a lot of trouble for machine learning algorithms. Also, if we perform the random sweeps in these parameter spaces, we can see that CST parameterization can create a very unphysical aerofoil shapes. Further, if we will do the sweeps, coordinate aligned sweeps in the PGA space, we can see that the aerodynamics quantities such as lift over drag, pitch and moment coefficient are changing very smoothly with the coordinate and also completely physical. The other advantage of the Grassmannian manifold usage is that we can define also 3D shapes, like a wind blade for wind turbines. Usually the blade represented by cross-section aerofoils, and we need to interpolate between them. Using the Grassmannian, we can just use the piecewise geodesic interpolation between the Grassmannian shapes, and then pair it with a spline for affine transformations. Moreover, we can do the perturbation, consistent perturbation along the blade by parallel transport the perturbation from one airfoil to the other. Thank you for your attention.